Hello and welcome back. In this video we're covering section 8.2 on the law of sines. This will also be followed by 8.3, which is on the law of cosines, and each of these sections deal with the trigonometry of non-right triangles. So far we've been working with triangles where one of the angles is 90 degrees, and that's part of how we defined our trigonometric functions as relationships between the sides of these right triangles. Well, as we know, this is only a subset of all possible triangles, so we could have any number of triangles where there isn't a 90-degree angle inside of it. So we'll be able to apply some trigonometric properties to these triangles through the law of sines and the law of cosines, and we'll start with the former in this video. So let's take a look at what we'll define as the law of sines. So we have this statement here. For a triangle with side lengths A, B, and C, and opposite angles A, B, and C, respectively, we can say the sine of angle A divided by side length A equals the side of angle B divided by side length B, which is also equal to the side of angle C that's divided by the side length of C. So let's draw a picture of what this is describing. So we can have a non-right triangle, so something like this. And so let's call this angle A. So that would make this opposite side side length A. We can call this angle B, so this would be side length B, and let's call this angle C, so this will be side length C. So it's saying that the sine of this angle divided by its opposite side length should be equal to the sine of, say, this angle divided by its opposite side length, or any other combination of those. So let's show how this would be true just for one of these cases, and then we can apply the same idea to the others. Let's start by drawing a vertical line from the top of the triangle down to its base so that we create two right triangles. And that's sort of the general trick here. So let's describe, and let's call this height just h for the height. So let's describe the sine of A, sine of angle A. Well, using right angle trig, that's the opposite side length divided by the hypotenuse. So we can define this as this height h divided by side length c. So here we could solve for h by multiplying the c over. We can say the height of this triangle would be c times the sine of A, of angle A. And let's do a similar statement for angle C. Let's take the sine of angle C. Well, that would be opposite side length, which is h, divided by the hypotenuse of A. So opposite side length is h divided by A. And we can solve this for h as well. We can say h equals A times the sine of C. And since these are both equal to h, they must be equal to each other. We can say C times the sine of A is equal to A times the sine of C. And then if we divide this A over to the other side and take this C and divide it to the other side, we get one piece of our law of sines. We can say the sine of A, sine of angle A over side length A should equal the sine of angle C over side length C. So we get these two pieces equal to each other. And we can do a similar argument, say if we draw a straight line from this angle to create two right triangles, we can create a similar statement linking the sine of B and the sine of C. Or if we drew a straight line here, create two right triangles, we can relate the sine of A and the sine of B. So we could go through that same process. So we get this useful property where we're able to solve side lengths and angles of triangles that aren't necessarily right triangles. So in the second box, they give all different combinations between A and B, between A and C, between B and C. So it's true between all angles of the triangle. And then let's also keep in mind this fact that the sum of all three angles within a triangle, regardless if it's a right triangle or not, should add up to 180 degrees. So this will allow us to now solve many additional triangles as opposed to just right triangles. So let's take a look at an example. So example 1 says using the law of sines to solve an SAA triangle. What this is referencing is the information that's given. We're given one side and two angles, so SAA. So that's what they tell us here. We have two angles and one side length. And to solve a triangle, that means to find all angles and all side lengths. So we're looking to find, we already know what angle A is, 40 degrees, but we're trying to find side length A. And we know what angle B is, 60 degrees. So we're trying to find side length B. Oh, and we're actually given side length A, so let me place this in here. This would be 4. And we don't know what angle C is, and we also don't know what side length C is. So we have those three missing pieces that we need to find in order to solve this triangle. So since we have two angles, it's pretty easy to find that third angle. So that can be the first thing we do. We can find angle C. Let's just use the fact that they should all sum up to 180 degrees. So if I say 40 degrees plus 60 degrees plus whatever angle C is, this must equal 180. So that means C would be equal to 180 minus 40 minus 60. So that means C is equal to 80 degrees. Because 60 plus 40 is 100, so 180 minus 100 is 80. So we got our third angle. Now let's use the law of sines in order to find our two missing side lengths. So let's start with, let's try to find side length A. So or no, I'm sorry, let's find side length C. I keep saying we don't know A. Let's find side length C. So we know angle A and side length A. We now know angle C as 80 degrees. So let's use the law of sines relating angle A and angle C. Meaning we can say the sine of angle A over side length A should equal the sine of angle C over side length C. And let's plug in everything that we know. A is 40 degrees, so this would be the sine of 40. Side length A is 4. We just found out side length C, which is 80, so we can say sine of 80. And we need side length C. So if we rearrange this a little bit, if I multiply the C over to the other side, maybe I'll write this out. So I would get C times the sine of 40 over 4 equals the sine of 80. And now let's multiply the 4 over and then divide by the sine of 40 to get a statement for C. we can say C equals 4 times the sine of 80 degrees divided by the sine of 40 degrees. So this we can type into our calculator, just be sure that it's in degree mode. That will be the main thing. If it's in radians, then we'll get an incorrect answer. We'll get something different. So as long as you're in degree mode, you can type this in, 4 times the sine of 80 degrees divided by the sine of 40 degrees. And that should give you approximately 6.13. We do a little rounding. So we have one of our missing side lengths. Now let's find the others. We're just looking for side length B. So we could say something similar. We can say like the sine of B, or I'm sorry, the sine of A over side length A should equal the sine of angle B over side length B. So let's plug in what we know. Let me scoot this over, make a little more room. So let's plug in what we know. Angle A is 40 degrees. So this is the sine of 40 over side length A, so over 4. This should equal the sine of 60 degrees over some unknown length B. So rearranging this, we would get that B equals 4 times the sine of 60 divided by the sine of 40. So if we plug all of that in, you should get that B is approximately 5.39. So we were able to find our missing angle, and that was pretty simple just by subtracting the other angles from 180. And then we found our two missing side lengths using the law of sines. So just look through what you have available and see what you can produce where you know all the other components, like we knew angle A, side length A, and we found angle C, and we're wanting to find this remaining side length C. So that'll help you decide which ones to pick. All right, let's look at one more example. So we're given two angles and one side. So we can say angle A is 35 degrees, but this time we don't know side length A. Angle B is 15 degrees, but we don't know side length B. We don't know angle C, but we know side length C as 5. So first, we'll start over here. Let's find angle C. Just like we did before, we can take and say C should be 180 degrees minus our two other angles. So minus 35, minus 15. So we should get that C is equal to 130 degrees. So we have our missing angle. Now let's try to find side length A. So we know our angle for C and side length C, and we know angle A, just don't know side length A. So let's build a law of sines statement using A and C. So we can say the sine of A over A should equal the sine of C over C. So we can plug in what we have. The sine of 35 degrees over A should equal the sine of 130 degrees over C. Oh, and we know what C is. C is equal to 5. So rearranging for A, we're going to be multiplying this A over and then multiplying this 5 over here and then dividing by the sine of 130. Just do a few steps in one. We should end up with A being equal to 5 times the sine of 35 degrees divided by the sine of 130 degrees. So just a little algebraic manipulation, just flipping things around. So plugging all that in degree mode and doing a little rounding should get that A is approximately 3.74. All right, let's do something similar for our last missing piece, which is side length B. So I'm going to stick with using C. So let's relate C and B. We could do it between B and A, but since we did some rounding here for side length A, it might introduce some additional slight errors. So if you can avoid using a value that you had to round with, that would be ideal. Sometimes that's not possible, but we do know this side length for sure didn't have to round, and 130 degrees we didn't have to do any rounding either. So this will give us our most accurate result. So let's relate B and C. We can say the sine of angle B divided by side length B should equal the sine of angle C divided by side length C. So plugging in, that will be the sine of 15 degrees over unknown side length B equals the sine of 130 degrees over 5. So rearranging again, we should get that B equals 5 times the sine of 15 degrees over the sine of 130 degrees. So plugging that in, doing a little bit of rounding, we get B is approximately 1.69. So we found our missing angle by subtracting the others from 180. Then we found our two missing side lengths using the law of sine. So similar to our last one. So that's if you're given two angles and a side length. So how about if we're given two sides and one angle? So we'll call this an SSA triangle. So this can produce some peculiarities. We have some special cases here, and we'll see how that will come up. So let's just look at this first one, example 3. We're given two side lengths and one angle. So we don't know angle A. That'll be a question mark. We know side length A is 2. We don't know angle B. We also don't know side length B. We know angle C, but we don't know side length C. So what can we do? Oh, we do know side length C. They give us positive 1 here. Yes, we know AC and angle C. So let's approach it as we would normally. We can't find a missing angle yet because we don't know two of our angles. But let's try to set up a statement using the law of sines, maybe relating angle A and angle C. And then maybe we can do some inverse trigonometry to find out what the angle should be. So we can say the sine of A over side length A should be equal to the sine of C over side length C. We don't know what angle A is, so we'll leave that as the sine of A. Side length A is 2. We know what the sine of C is, or we know what angle C is, that's 50 degrees. And side length C is 1. So multiplying the 2 over, we get that the sine of A equals 2 times the sine of 50 degrees. So if we evaluate this right side, that's something we can plug in, then maybe we can take the inverse sine of both sides and find out what our missing angle is. So that's one technique we can use to find a missing angle. So when we evaluate the right-hand side, if you do 2 times the sine of 50 degrees, you should get approximately 1.53. And let's see, if we try to take the inverse sine of 1.53, you get a domain error in your calculator. So keep in mind from the perspective of the sine, what the range of the sine is. Like, what are all possible output values of the sine function? We had said previously that the range of the sine was between -1 and +1. Or from a graph perspective, the sine wave had a maximum value of 1, minimum value of -1. So to say that the sine of some angle equals 1.53, which is greater than +1, wouldn't make any sense. It's something that's outside the range of the sine function. Or if we were to take the inverse sine of both sides, we'd say A equals the inverse sine of 1.53. But it's kind of saying the same thing, but the domain of the inverse sine is between -1 and +1. So it's not something we can even plug in. And you'll see that if you try to do this on the calculator. So in this case, there's actually no solution, and they kind of gave that away in the problem description. But that is something you could run into, meaning there's no triangle that would have these these particular properties. So in this case, we'll just have to say no solution. So let's look at example 4. Notice this one says one solution, and in our next example, there's a variant of this where we have 2 possible solutions. So let's look at the one solution problem. And I'll start it out the same. I'll write out what we know and what we're trying to find. So we're given angle A. Angle A is 40 degrees. And we are given side length A, which is 3. We don't know angle B, but we know side length B. And we don't know anything about angle C or side length C. So let's just pick something to try to find. Let's try to find angle B. So let's set up a law of sine statement relating angle A and B. So we can say the sine of 40 degrees divided by 3 should equal the sine of angle B divided by 2. So if we multiply the 2 over, we can say the sine of angle B would equal 2 times the sine of 40 degrees divided by 3. So if you evaluate that right side, we get that the sine of angle B equals 0.43. So a positive value. And it's less than 1, so it is a legitimate value. We would get some kind of solution here. But something to note is that there's actually two angles that can possibly produce this value. When we take the inverse sine of both sides, which is what we can get to find b, keep in mind that the range of the inverse sine will only give us values between negative 90 degrees and positive 90 degrees. So negative pi over 2 and positive pi over 2. So we'll only get values in this particular range. But as we know from working with the unit circle a lot, there's two different angles that will give you the same sine value. One is in the, and if they're both if the value is positive, there's an angle in the first quadrant that will give you that sine value. But there's also an angle in the second quadrant that will give you the same sine value. But when we take the inverse sine, we'll only get one of those angles, the one that's in quadrant 1. So we need to also consider, is there some other angle that will also give us the same value? There might be two triangles that have these potential properties. So we need to evaluate and do a little bit of thinking to determine if we should consider a second solution. So let me jump down here. So if we have, I'll rewrite what we have. The sine of b equals 0.43. So let's take the inverse sine of both sides, and we can say that b equals the inverse sine of 0.43. So if you type that in and you're in degree mode, you should get approximately 25.4 degrees. So that would be our angle in the first quadrant. So that is definitely one solution for our angle B. So we can say B equals 25.4. But let's consider the angle in the second quadrant that would produce the same sine value. And using this diagram, if this angle here is 25.4 degrees, we would want this angle going into the second quadrant. And just thinking symmetrically, this space here, this angle would also be 25.4 degrees. So if we want that larger angle, we can take 180 and subtract the 25.4. Because this whole angle here is 180, and if we subtract this smaller angle, we'll get the angle that we're looking for. So our second option would be, we can say, or maybe b equals 180 degrees minus 25.4, which is 154.6 degrees. And we need to stop and do a little bit of reasoning to see if this is a reasonable angle. So keep in mind that all three angles must add up to 180 degrees. And if one of our angles is 154.6, and we know our other angle from earlier was 40 degrees, if we just add those two together, we will already be beyond 180 degrees. We'll be at like 194.6. So there wouldn't even be any room left for our third angle. So in this case, we would disregard this second solution. It wouldn't be a reasonable angle in the context of being inside of this triangle. So here, there's a potential for two solutions, but since this produced an unreasonable angle, we'll just stick with this first solution. That one will work out for us. But we'll see in the next example where we'll get two possible solutions. So let's continue with this one angle for angle B. So let's find angle C. So now that we know two of our angles, we can find angle C just by subtracting our two knowns from 180. Should be 180 degrees minus 40 degrees minus 25.4 degrees. So you should get that C is equal to 114.6 degrees. So now we know angle B, we know angle C. Let's just find our missing side length, C. So we can relate angle C and angle A. So we can say the sine of angle A, which is 40 degrees, over side length A, which is 3, should equal the sine of angle C, which we just found to be 114.6 degrees, over our unknown side length C. So a little bit of rearranging should get that C is equal to, let's see, 3 times the sine of 114.6 divided by the sine of 40 degrees. So evaluating this, you should get that C is approximately equal to 4.24. So we found our two missing angles and our missing side length. And when you do this, if you have a particular problem where you end up having to find one of the missing angles using an inverse sine function, keep in mind that there might be two potential solutions. That's what we had here. And when you produce your two potential angles, so we said 25.4 or possibly 154.6, just verify that they are angles that would produce a legitimate triangle. Meaning if you add this to your other angle, do you get something beyond 180 degrees? There has to be room for our third missing angle. So let's see how that will show up in our next example, where we will be able to get two possible triangles. So let's see what's given. They say angle A is 35 degrees, and we know side length A is 6. We don't know angle B, but we know side length B. We don't know angle C, and we don't know side length C. So let's approach this in the same way. Let's try to find angle B. So let's create a law of sines statement between A and B. So we can say the sine of 35 degrees over 6 should be equal to the sine of B over 8. So multiply the 8 over and we get the sine of B should equal 8 times the sine of 35 degrees divided by 6. If you evaluate the right side, we get that the sine of B is approximately 0.76. So let's take the inverse sine of 0.76 and you should get 49.9 degrees. So that's one possible solution for this angle. So we can say, I'll call it B1. B sub 1 is 49.9. So let's do that same trick as last time. If we want the other angle, the angle in the second quadrant that would have the same sine value, we can just subtract this angle from 180 degrees. That should be our second value. So, or potentially, I'll say B2 would be 180 minus 49.9, which we get 130.1 degrees. So I'll just check. If I add 130.1 and 35, do I get something that's beyond 180? So 130.1 plus 35, we get 165.1. So there's still room for our third angle. So in this case, we will have two potential triangles because we have two different side lengths for our, two different angles for angle B. So we'll need to build two cases. So let's take our first case. I can say for when we have B, our first B angle, B1, B equals 49.9 degrees. Let's find what angle C would be if B is 49.9. So I'll call that C1. That should be 180 minus 35 minus 49.9. So C1 should be equal to 95.1 degrees. And then let's find what the associated side length C would be. In this case, I'll call that little c1. So I'll use law of sines between A and C. So I can say the sine of angle A, which is 35 degrees, over side length A, which is 6, should equal the sine of our new angle C, 95.1, over side length C. And I'm calling it C1 because it's going to be one of our two solutions. So rearranging, we get that C sub 1 would equal 6 times the sine of 95.1 over the sine of 35. So evaluating that, we should get 10.42. So that's for our first solution when we have this first angle for B. So let's do the same thing with our second B angle to produce our second possible triangle. So I can say this will be when B equals 130.1 degrees. So let's do the same thing. So now let's find C2. So take 180. We'll still subtract 35, but now let's also subtract 130.1. So this should give you 14.9 degrees. And then let's find what its associated side length would be. So I can say the sine of 35 degrees, so I'm going to relate A and C again. Sine of 35 over 6 should be equal to the sine of 14.9 over C1. Or I'm sorry, over C2. So rearranging, C2 should equal 6 times the sine of 14.9 divided by the sine of 35. So evaluating this, you get C2 should be 2.69. So this was another example where we're given two side lengths and an angle. You have to find one of the angles in this way using the inverse sign, and that produces two possible solutions. So the first one usually works out fine. The second solution, the one that's in the second quadrant, you have to check if it's a legitimate angle for a triangle, if when you add it to one of your known, like the known side length, if there's room for your third angle. So it shouldn't be greater than 180 degrees. Um, so if there's still room for your third angle, then you get two solutions. You get two possible triangles. So you just take your first possible angle and then complete the process using that, and then come back and take your second possible angle and find the remaining information using that one. So it gets a little bit trickier when you have two sides and an angle. So let's see how we can use this law of sines to solve a couple of applied problems. So the first one is called finding the height of a mountain. It says to measure the height of a mountain, a surveyor takes two sightings of the peak at a distance of 900 meters apart on a direct line to the mountain. So let's imagine this is the peak of the mountain up here, and we're trying to find how tall it is. And they're saying they take one measurement, so let's imagine the measurement right here is taken. So they're measuring the angle of elevation up to the peak of the mountain. It says the first observation results in an angle of elevation of 47 degrees. So we can call this angle 47 degrees. And this will be a right angle here. Then it says that the two angles were 900 meters apart, meaning they take this first angle and then they walk backwards 900 meters and then take a second reading. So imagine another angle is taken, and this time it's 35 degrees. And it says the transit is 2 meters high, meaning that's how tall the person is, because they're doing this from eye length. So we would have an additional 2 meters that we would need to consider on top of this height that we'll find using these triangles. So we have some distance that we're finding, but this was taken at eye length, at eye height, which is 2 meters above the ground. So we'll have to add that additional 2 meters in. So you might, in maybe some previous version of this question, if we knew exactly how far we were away from the mountain, we could just use a single triangle and have some angle. And if we knew how far away we are, we can maybe use the inverse tangent to find our missing height. But it's probably hard to figure that out if you're measuring the height of a mountain. You'd have to first be at the base of the mountain, which you could argue how could you get there if it's a three-dimensional object. And you'd have to hike some like known distance away. So it's probably harder to find out that information. But if you just take two separate readings, take one reading, you can measure how far you walk backwards and take a second reading. And we'll see how we can use this in order to solve for this missing height. So again, this is the peak of the mountain here, and we have our two readings. So let's add some additional labels. Let me just call this angle C, and I can call this side length C. And we know this distance is 900 meters. So let's see what we can do. Let's see how we can find this out. Let's just start trying to find out what we can know. Like we can find out what this angle C is, since we know this angle is 47 degrees and it's along a flat line. So they should sum up to 180 degrees. So let's start there. we can say that C should equal 180 degrees minus 47 degrees. So that tells us that this inner angle is 133 degrees. And let's call this angle here A. So we know in this triangle, so imagining this triangle to the left side, we know two of the angles. So let's find our third one. We can find angle A by taking 180 and subtracting our known angle of 35, and then we just found this other angle, 133 degrees. So this tells us that angle A is 12 degrees. So if I find out this side length C using this non-right triangle, then I can imagine just the total triangle where I have this 35-degree angle. We want to find the height, and so it would be useful to find this side length because then we can say the sine of 35 degrees would be the height over that side length C. And then we'd be able to solve for the height. So let's find this side length C using the law of sines. We can say the sine of angle A, so the sine of 12 degrees, divided by, this would be side length A, the side length opposite of that angle, which we know is 900, meters, 900 meters, should equal the sine of angle C, which we just found angle C is 130 degrees, or 133 degrees, divided by our unknown side length C. So let's rearrange that. We should get that C equals 900 meters times the sine of 133 degrees divided by the sine of 12 degrees. So plugging all of that in, you should get that C is equal to 3,165.86 meters. So that's a useful piece of information. Now we can think of the entire triangle. So we know this side length, 3,165.86. So that means we can plug in for C here. We can say the sine of 35 degrees is the opposite side length of H over the hypotenuse of 3165.86. So H should be equal to the sine of 35 degrees times that hypotenuse. So if you plug that in, sine of 35 times 3165.86, and let's round to the nearest meter. We get that H equals 1,816. Yeah, 1,816. But let's keep in mind this 2-meter height here. This reading was taken at eye level. So we would just need to add 2. So we can say the height of the mountain should be 1,818 meters. So an interesting use of trigonometry to find some pretty unmeasurable distance, especially without more technical tools. You can do it with pure trigonometry. All right, let's look at one more applied example. So it's titled Rescue at Sea. It says the Coast Guard Station Zulu is located 120 miles due west of Station X-Ray. So let's imagine two stations on the coast. I'll call this one Zulu, and let's call this one X-Ray. And we know they're 120 miles apart. It says a ship at sea sends an SOS call that is received by each station. So let's imagine there's some ship. We'll call this being out in the sea, and it sends an SOS signal. It says the call to Station Zulu indicates that the bearing of the ship from Zulu is 40 degrees east of north. So that's what this notation means. Meaning if we imagine a line going straight north of Zulu, then the ship is 40 degrees east of it. So if I imagine a straight line going from Station Zulu to the ship, they're talking about this angle here. This is the angle east of north. Then it says the call to Station X-Ray indicates a bearing of the ship 30 degrees west of north. Meaning if I imagine a line going north, Station X-Ray, it's a 30-degree angle west of that, so in the clockwise direction. So they're talking about this angle here. So with this information, we can find two of these interior angles of the triangle, since they should, like this should add up to 90 degrees. So that means this must be a 50-degree angle. Same thing here, this should add up to 90 degrees. So this must be a 60-degree angle. So let's see what it's asking us. It wants us to find how far each station is from the ship, meaning those missing side lengths. So first, let's just find our missing angle, because that will probably be useful. Since we know two of the angles, we can just subtract them from 180 degrees. So let's call this angle C. Let's call this side length A, and let's call this side length B. So I can say C should be equal to 180 minus 50 minus 60. So that gives us 70 degrees. All right, so let's find our missing side lengths now. So I can use the law of sines. Let's relate two angles. Like let's relate the 50-degree angle and our 70-degree angle. I can say the sine of 50 degrees divided by the length opposite of that, which is our missing side length A, should equal the sine of 70 degrees, that's our C angle, divided by 120, because we know that side length. So if we rearrange things, we get that A is equal to 120 times the sine of 50 over the sine of 70. And if you evaluate this, you should get that A is approximately 97.82 miles. So that's the distance from the X-ray station. Then our second one, let's find this other missing side length. So we can build a similar statement we can say the sine of 60 degrees over the missing side length b should equal the sine of 70 degrees over 120. So rearranging this, we get that b is equal to 120 times the sine of 60 over the sine of 70. And evaluating that, we get approximately 110.59 miles. So this would be, that's this side length, so that's the distance from the Zulu station. So that was part A. Part B says, if a helicopter is capable of flying 200 miles per hour, is dispatched from the nearest station to the ship, how long will it take to reach the ship? Well, we found, let's see, the closest station was side length A, so that's from X-ray. Let's say X-ray is the closest station at a distance of 97.82 miles. And the helicopter is flying 200 miles per hour. So how long would it take them to get there? Well, if I know distance is rate times time, if I know something is going 200 miles per hour and it flies for some amount of time, some number of hours, that'll give me the distance that it traveled. Well, we can rearrange this and say the amount of time that goes by is equal to the distance traveled divided by the rate. So our time should be the distance of 97.82 miles divided by the rate of 200 miles per hour. That gives us about 0.49 hours. And so if we want to express this in terms of minutes, we would multiply by 60. So there's 60 minutes per hour. So 0.49 times 60 gives us, and I'll stick it in here, 29.4 minutes. That's how long it would take for this helicopter going 200 miles an hour to travel from this closest station to where the ship exists. So pretty cool use of the law of sines involving this non-right triangle to solve some missing side lengths, but in the context of this rescue at sea. Alright, that was the last example. So in this section we were introduced to the law of sines. So we solved triangles that involve two known angles and a side length. That was a more simple example. Just use the law of sines a couple times and find the missing angle by subtracting the others from 180. It got a little tricky with the side-side angle. So given two sides and one angle, either we had no solution or one solution or two solutions. So this had some extra complications. And then we got those extra applied problems at the end. Alright, that's it for this video, and I'll see you next time.